Okay, let's work through a little example of hydraulic head. We'll measure the hydraulic head of this body of water here. So in this example, we have a cylinder, and the top half is filled with water, and the bottom half is filled with sand. And there's a little divider in between the two and a plug right there in the middle. Okay? So let's figure out the hydraulic head of this body of water. Okay? And to do that, let's measure it right at the plug. And let's call that C. And let's say this height is 10 meters. And we'll say this one is 5, and then 0 down here. So this is our datum. And we have 5 feet of water above 5 feet of sand, okay? So let's write out our equation. Total head of the system, of the body of water, will equal our elevation head at C plus our pressure head at C. Okay, so let's figure out the elevation head at C. So this body of water is standing 5 meters above our datum here at 0, right? And if we pull this plug, we know this body of water is going to drop through the sand and hit the bottom there, right? And so our measuring point C here will wind up down here at the bottom, right? The bottom of the body of water will be at the bottom of the cylinder when we pull the plug. And so that's a 5-meter drop. So that is our elevation head, right? 5 meters. Now let's look at our pressure head at C. Well, how much water is on top of our measuring point there at C? It's 5 meters, right? There's 5 meters of water above our point C that are exerting pressure on our point C, right? So that's our pressure head. It's 5 meters of water exerting pressure on our point that we're measuring. So our pressure head at C is 5 meters. So back to our equation, our total head equals 5 plus 5, which equals 10 meters. Pretty simple, right? It's nothing too drastic, nothing too crazy. Now this will come in handy when we're talking about hydraulic gradient and head differentials, which make up a hydraulic gradient. I'll post that video in the comment section. I hope this video is pretty helpful. It's pretty simple and pretty basic, but it's important to understand the basic concept.
All right, so we're going to start off with our first activity, which is looking at different types of soil to see how the flow rate changes throughout them, depending on their K-sat. So we have a clay, a sand, and then a sandy loam, and they all have about 25 millimeters of soil in them, so they all have the same soil depth. And I'm going to pour about 15 millimeters of water into each of them at the same depth. So it'll be about the same depth or so. Let me pour a little bit more in this one so they're all equal. But basically, it's kind of hard to tell because we normally will do this over a few minutes. But the sand is having the highest amount of flow rate, whereas the clay has the lowest amount of flow rate, and then the sandy loam is about somewhat in the middle. Basically showing that as long as you have the same amount of water and the same amount of soil, the K-sat is what's going to depend and change how quickly the flow goes through the soil. So that's our first activity. All right, and this is activity 2, where we'll have the same soil, the same amount of water, but we're differing the amount of soil that we have. So that is the variable that we're changing in Darcy's Law. So I'm going to pour the same amount of water in each of these columns. And we'll give it a little bit of time to drain, but basically what you'll see is that this one is going to drain the water faster than this one because there's less soil for it to go through. So again, changing that variable in Darcy's Law. Same type of soil, same amount of water, different amount of sediment that we are testing. So this one will drain faster than this one. So that finishes activity 2. All right, so for activity 3, we are going to be changing the amount of water, the water depth in each of our cylinders. We have the same depth of soil and the same type of soil. The only thing that's changing is the amount of water. I'm going to put in about double the amount of water in this soil column as I do in this one. If I were to sit here in time, how long it takes for all the water to come out of the soil columns, I would see that this column here takes double the amount of time to drain as it does this column. And that's because there's double the amount of water that is in this column as compared to this column. But the flow rate, if we were to divide that time over the amount of water that we collected out of the column, is the same. So this basically shows that the amount of water that is in a soil column does not affect the flow rate, but it does affect the amount of time that it takes to drain out. So this is activity 3. All right, so for our last activity, we're going to look at the pressure head in a saturated soil. So here I have what's going to be our piezometer that we're going to use, and then just a jar full of sand. And so what I'm going to do is I'm going to stick the piezometer down into about where this black line is. And what we're going to do is I'm going to get some water, and I'm going to pour in the water until we have a little bit of ponding above the soil surface. You gotta wait for it to be saturated. A little bit more, probably be good. Okay. So, if we're looking at our system right here, the straw is lined up at the bottom of this black line. And so when the soil is saturated with ponding water at the top, if we were able to look inside the straw, the entire amount of water that is in the system would be from the black line all the way up to the top of ponding. And this basically represents that we have positive pressure head at the depth below this water surface. And so if we were to slowly lift up the straw to the top and have it sitting on top of the soil, now the water depth that is in the straw is just the freestanding water, ponding water that's on top of the soil. So the depth of the water in the straw should be equal to the ponded water depth at this top. This shows that the pressure head at the soil surface equals the height of the ponded water. And now if I were to pour some of this water out, so we have no ponding water, and if I was just to set this back on top of the soil, there's no more water in it. That basically shows that there's no pressure head that's happening because there's no water above the top of the soil. So this is basically just to show that the pressure head in a saturated soil depends on the amount of water that's in the soil and then also the soil itself. So in conclusion, in a saturated soil, the pressure head of the water at the piezometer intake zone is equal to the depth of water in the piezometer, and the water in the soil that is in contact with the atmosphere has a pressure head of 0. So if there's no ponding water, we have no pressure head. So that's our last activity for the lab. Sorry we couldn't do this in person, but hopefully this makes Darcy's Law make a little bit more sense.